All right, good morning. So maybe it's not morning for you. It's probably evening for you, but it's morning for me, so good luck with this anyway. So today we're going to talk about some simple ionic compounds. We've learned how to make ions in the last, or kind of how ions get their charges, I guess, in the last little piece. And here we're going to start kind of sticking them together like Legos and figuring out how to make some basic compounds. We're not going to go real far with this, just some very simple small molecules or small ionic compounds. Chapter 4, our next one that's coming up, is all about creating names and formulas. So we've got plenty more of this to come here. So what we got going on here, some basic vocabulary. First of all, cations and anions. Cations are positively charged, and like sodium atoms, they become ions by losing an electron. So I found my little red pointer. I'm very excited. Over here you can see this one outer shell electron that sodium has, and it gets rid of it to become the sodium ion. And in the sodium ion we can see that it's gone in that particular little shell diagram. Anions, on the other hand, nice English. On the other hand, like oxygen down here, they become ions by gaining electrons. So here, if you take a look at this outside ring on oxygen, it's only got 6 electrons when it really wants to have 8 to be stable. So when it transitions over to this oxide ion, you can see now that it's full. It's gained a couple of electrons from somewhere and is now an oxygen ion, also known as oxide. So, second part of review for this, if you don't have your periodic table out, you probably want to grab one and have one nearby. Maybe have it up on your phone, whatever you want to do. Maybe don't have it on your phone, because then you're just going to look at stuff on your phone. But have a periodic table out of your notes open that's got that pattern of charges. And again, that's that shortcut that we're going to use here today to make our lives a little bit easier. So again, the idea of the charges is that we've got these this numbering system for these tall columns where they're either +1, +2, +3, plus or minus 4, 3, 2, 1, and then 0 down on the negative side. So again, make sure you've got that around. We're not going to worry about the center part of the periodic table here where it says this part gets concentrated, those transition metals. They're all cations, but they've got a variety of charges, so we don't have to worry about those until the next chapter. Okay, so what we're talking about here is now the formation of ionic bonds. The last one we kind of talked about what happens when ions form. Here we're talking about what happens when ions come together. How can we predict the formulas of these things when they come together one-to-one? So we looked at this particular image of sodium and chlorine ions, these guys over here, last time, where we had a sodium atom that had that 1 extra electron and a chlorine atom that had 7 electrons in its outer shell. And that whole idea of transferring the electrons, giving it up, sodium giving it away, becoming sodium ion, and then chlorine receiving that electron to become chloride or chlorine ion. And so how do we figure out the formulas from these things? So a couple of things. Number one, if you know how many electrons they have to give and take, it can help you kind of understand how these bonds are formed. In this particular case, it's perfect because sodium has 1 and chlorine needs 1. So it's a perfect example of them kind of in a 1-to-1. These two ions get formed as soon as that electron gets transferred. So as soon as sodium gets away or gives away its electron, it becomes sodium ion. As soon as chlorine gains an electron, it becomes chloride or chlorine ion. And then as a result of those two things having opposite charges from that transfer of electron, now they stick together like magnets. One's positive, one's negative, and opposites attract. So that piece of a positive and negative coming together is what we call an ionic bond. It's electrostatic attraction, but that idea that opposites attract. So two positives won't stick together, they'll repel. Two negatives won't stick together, but a positive and a negative will come together. And the plus charges, like +2, +3, it's kind of like the size of the charge that they've got, whether they're more attractive or less attractive, I guess. More repulsive? That sounds terrible. So when these two things come together, when we've got sodium ion and chlorine ion together, we call that new thing a compound. And we've talked about that before. And in this case, they partner up in a 1-to-1 ratio. Every sodium has 1 chlorine partner to it. And we start to get a lot of these things together. We get these solid compounds, ionic compounds, like salt. So that big picture down in the center down here is kind of what salt looks like at the ultra microscopic level, where if we just had a grain of salt, there would be alternating sodium and chlorine, sodium and chlorine, sodium and chlorine in a 3-dimensional shape where they're all packed together in that solid form. This is not what happens when salt dissolves in water, where the two ions can separate and kind of go their own way, but we'll get to that in a later particular content. So with this one, again, key points in this particular one, that idea that they're 1-to-1, that every 1 sodium, there's 1 chlorine to it. We would write that formula then as a 1-to-1 as NaCl. We don't have to write the charges in here when we're writing compound formulas, because they would get really long and crazy. But this tells us that there's one sodium and one chlorine that are kind of bonded together. And when we stick them together like that, for right now, we can assume that those are ionically stuck together because of plus-minus charges. And then we would name this thing as sodium chloride. Again, that ending IDE, that tells me that those are stuck together in a compound. It's not sodium, metal, and chlorine gas. It's this new compound, sodium chloride. So that IDE ending does become important. So watch your spelling on that. Okay, kind of moving forward, next step. What if it's got different charges to it? So this particular example takes a look at two different ions, which is magnesium and oxygen's ions. And in this case, they have a slightly different pattern. So you may remember this from your periodic table, but magnesium atoms up here, they become a +2 ion. And again, the reason for that, here's that +2 ion right there. The reason for that is that they've got those 2 electrons on the outside energy level that they want to get rid of. And then oxygen atoms become oxide with also a 2- charge. And again, the reason for that is it gains those 2 electrons to fill up those spots right in there. So again, we've got magnesium ion and oxide ion, 2+ and 2-. So what happens when these guys come together? Again, it's a perfect partnership. Magnesium has 2 to get rid of, oxygen has 2 to receive, and so they can actually form a 1-to-1 relationship as well. They're happy just the way they are. So you get a 1-to-1, 1 magnesium, 1 oxide. So the formula for this is exactly like it sounds, MgO, 1 magnesium and 1 oxygen. And the name of this is magnesium oxide, IDE, again, because it's that oxygen ion as a negative ion. It's not always this easy, unfortunately. So what happens if they don't have the exact same charge? So I'm grabbing 2 from previous screens that we've looked at. So here's our magnesium atom with its 2 extra electrons that it wants to get rid of. And then here we've got chlorine atoms with its 7 electrons. Remember, 8 is the magic number for stability, and it only has 7 there. So again, it wants to gain 1 electron. So what would happen if we have this picture down at the bottom? Magnesium is going to give away 1 of its electrons to chlorine, and that chlorine ion now, chloride, is happy. But what about the magnesium? Well, magnesium's not. This magnesium is now magnesium 1+, and it's still not stable. It needs to do something else to achieve that stability. It needs to get rid of both of its electrons. And so the trick here is that we have to have something else that goes on. And now in this case, it's magnesium not just with 1 chlorine. Magnesium's going to hang out with 2 chlorines. It's going to give 1 electron to one, 1 electron to the other. This is why magnesium becomes a 2+ and only a 2+. And then the chlorines, when they bond together, they form this kind of larger sort of molecule that's not the same as the ones that we've seen before. So in this case, if we have magnesium chloride, this particular salt, it's not a 1-to-1 like sodium chloride is. It's a 1-to-2. 1 magnesium is going to bond up with 2 chlorines. And that's a little bit different. But it kind of makes some sense in terms of the way that electrons are being transferred. So now when we write this formula, again, it's not MgCl, it's MgCl2 because it's 2 chlorines. We have to have 2 of them there to finish that particular bit. But luckily for us, the names don't get any crazy yet. It's still just magnesium chloride, IDE, because it's magnesium ions and chlorine ions coming together. So just the name of magnesium chloride. Okay. Taking the shortcut. I don't want to draw these bullseye diagrams every time I have to do one of these problems, and I'm certain that you don't either, unless you really have some kind of sick fun that you like to enjoy drawing all these circles and dots and stuff. But we can use that shortcut, and this is that periodic table shortcut, so that we know what the charges are. And the big idea here is that when we combine these two things together, when we form these ionic compounds, key idea is at the end, the charges have to add up to 0. Now this is a molecule basically that is neutral, not the ions themselves, but the ratio of the ions is what kind of adds up to 0. So let's look at an example here, it'll make a little bit more sense. So if we've got sodium and chlorine, then we've got a sodium's a 1+ and chlorine's a 1-. So as we're starting to work on putting these two things together, we can kind of figure out how do we add them up in such a way that we have a 0 net charge at the end. And in this case, it's pretty easy because we have a 1+ and a 1-. 1 and 1 already adds up to 0. So we're kind of good on that one. And our symbol, our formula for our compound here, is just one of each, NaCl. And that's the one that we looked at earlier. But what happens if we have the magnesium 2+ and the chlorine 1-? So again, without drawing all the bullseye diagrams, we'd look at those charges and try to figure out what's happening with those. So the magnesium's a 2+ and the chlorine's a 1-. If we just try to add those up, it doesn't add up to 0 yet. 2+ and 1- is not neutral, that's a 1+. So we have to take a look at what do we need to do, how can we modify the numbers of each of them to get them to completely balance out. And in this case, it just means that we need 2 chlorine ions to balance out that +2 charge from the 1 magnesium. And so we would write our formula as MgCl2, telling me that there's 2 of the negative charges and 1 of the +2 positive charge. And that adds up to 0. So that's how we would write that formula. Okay. For you guys, that's kind of the long way. Here's the short, even shorter way. We're getting short, shorter, shortest. Here's the shortest way to do this. If you want to figure it out long way, perfect. The shortcut, super shortcut, is that we can use this process called crossing down. I don't know if that's a formal name, but that's what I call it. This idea of taking the charges and crossing it down to the bottom of the other one. And that's kind of what this little picture here tries to show. So we're trying to bond calcium ions, which are 2+, and chloride ions, which are 1-. We simply take the number of the charge and make it the subscript on the other element. So I would take the 2 from the calcium and make it a subscript of 2 on the chlorine, and I would take the 1 from the chlorine and make it, I guess, a subscript on the calcium. We don't need to write the subscript of 1. So it's a crossing down. You take the numbers and do it. You don't carry the charges, just like the absolute value, I guess, of that particular charge is what you go. So cross it down. The charge becomes the opposite element's formula, subscript number. So here's a couple of practice problems. I'll do the first one kind of slow, and then I'll let you kind of do the other two. So number 1, let's see if we can do this crossing down process to figure out the formula, what happens when sodium and sulfur ions come together. So this is sodium ion and sulfide. So here's how I would start this. I'd start by writing the symbols of the 2 ions. So there they are, sodium ion and sulfide ion. Again, I know those charges from looking at the periodic table. Sulfur is in the 2- column, so I know that one. Second thing I do is I think about crossing down. So I'm going to grab those charges, just the values of them, and move them to the opposite element, that crossing down. And then the last part is I'm going to write it as an actual formula. So that I would get Na2 and S. So that means there's 2 sodium ions to every 1 sulfur ion, and the name of that would just be called sodium sulfide. So this is a really good time for you to hit pause and see if you can scratch out the formulas for these other 2, aluminum and fluorine, and magnesium and phosphorus. So hit pause right now, and in 3, 2, 1, I'll come back and I'll do them for you. Here we go. Okay, so there's aluminum and fluorine. Aluminum is a 3+ from that particular part of the periodic table, and fluorine is a halogen, so it's got a 1- charge. So again, if you cross them down, grab those 2 numbers, stick them down as subscripts on the opposite side, now we get this, AlF3, and that's called aluminum fluoride. There's 1 aluminum and 3 fluorine ions in that particular molecule as it bonds together. All right, last one, magnesium and phosphorus. Magnesium is a 2+, and phosphorus is a 3-, and again, I got those from the periodic table patterns, or you can draw bullseye diagrams, however. And if I put these 2 things together, again, grab the numbers, cross them down. Now we've got an example here that has 2 subscript numbers, and that's perfectly acceptable as well. So this would be Mg3P2. I need 3 magnesium ions and 2 phosphorus ions, and they add up to 0. And if you actually do it, it's like it doesn't seem like it adds up to 0. Remember, each magnesium is a 2+. If I have 3 of them, that's a total charge of 6+ from those magnesiums. Phosphorus is a 3-, and if I have 2 of those, it's a total charge of 6- on those negative ions. So 6+ and 6- balances each other out. And again, that thing is called magnesium phosphide. Some people write it as phosphoride, but typically in the United States we write it as phosphide. So again, a little bit weird on there. Okay, so I'm kind of wrapping it up here almost at the end. Do's and don'ts. Here's all of our do's. Our kind of rules for writing formulas from ions and ion charges. Number 1, make sure you've got that periodic table in front of you, and use those columns to figure out what the ion charges are. 1, 2, 3, 4, -3, -2, -1, and then 0. You won't be writing any formulas of noble gases because they're noble gases. They don't participate. If you're going to do these when you're writing your formulas, always write the cation first. I know I didn't say that earlier, but if you look at all the examples that I've done, the cation always goes first and the anion always goes second. It's just kind of by a common agreement among chemists that we always put the cation first. Third thing is using that crossing down to make sure that you're stealing the charge from one and making it the subscript of the other. And then change the name of it. If you're going to write the name out, you write the 2 elements out, but the anion, you change its ending to IDE, ide, so oxide, nitride, phosphide, I guess you could have carbide, those sorts of things. Okay, here's some of the big don'ts. So be careful not to do the following. You do not need to write the number 1 as a subscript, so if something's a 1+ or a 1- charge, you don't have to carry that 1 over. I'm assuming that if that element's there, that there's at least one of them that's there. Number 2, make sure that you write the positive ion first. I guess I meant to write this as the opposite. Don't switch the order. Don't write it so that the negative ion is first. That's kind of what I meant to say. So don't flip them around just because you're doing the crossing down. Third and fourth one, I'll give you an example of what I mean by this. The third one here, you don't need to use subscripts. The charges are already equal. We only use the crossing down method if the charges are unequal and we need to figure out what the formula is. If you've got a 2 plus and a 2 minus or a 3 plus and a 3 minus, they're already balanced out just like that. They're in a 1-to-1 ratio. Again, I'll show you an example in just a second. And then the last one that's a don't, and this is a little bit tricky that you'll get quizzed on in a little bit. Make sure that if you have even numbers that you reduce them down, and I'll give you an example of what I mean. So like you would never write a fraction as 2/4, you would always write it as 1/2. Kind of the same idea. When you have even number subscripts, sometimes you have to reduce. So here's the two examples I'll put up here. So take a second and see if you can use those last two don'ts and see if you can figure out how to write the correct formulas for these. You might want to hit pause, but I'm about to go on and do them. They're the last two don'ts. So ready? All right, here's your two formulas. That Al3N3, we do not need to use subscripts for that because they're already equal charges, so they're going to be in a 1-to-1 ratio. Aluminum's going to give away 3 electrons. Nitrogen's going to take all 3 of them, so we don't need any weird subscripts for this. And then the last one, Si4 plus and O2 minus. Again, you need to reduce this one down. This is a perfect case of where it looks like you'd start off as Si2O4, but you can reduce that. I mean, you can think of the Al3N3 as a reducing example as well, where you're actually just kind of dividing both of them by 3. And in this case, the SiO2, you're dividing both of them by 2 to reduce it. So again, simplest possible formula that you can get, not necessarily the most complex one. So those are the last two are just kind of a couple of picky be carefuls. All right, so what did you learn today? Well, hopefully something, but anyway, here's what you should have learned today. If you're awake, wake up. Are you awake? Anyway, what did you need to know? Charges of ions are due to the gain or loss of electrons. So again, we had practice on that in the last one, just sort of reviewing it here. Second one, you should be able to use the periodic table, and again, those tall columns should have that +1, +2, +3, plus or minus 4, -3, -2, -1. Again, that's a review in this one, but I'm kind of highlighting that one more time. Here's a new one. Ionic bonds are formed from electrostatic attraction. So when we have ions that are giving and taking electrons and become plus and minus, that those ions then want to stick together. It's like they become magnetic. And when you put magnets near each other, they just automatically pop and they form those sort of ionic bonds. And it actually makes them really happy when they're like that. It's kind of a funny thing to think about that. Next thing that's kind of new is that when we're talking about these chemical formulas, those subscript numbers tell us something about the ratio. How many of the cations are present for every how many of the anions to it. And that's what the subscript numbers tell us. And then that big idea that they have to add up to 0 when we're figuring out what those ratios are. And that's the big rule, that they're always going to add up to 0 when we're writing these simple ionic compounds. So again, if you've got a 1 plus and a 2 minus, they don't add up to 0. You need to use some sort of a subscript number to get that to a correct ratio where they add up to 0. And then there's that shortcut method that we can use rather than kind of doing it the long way. You can use the crossing down method. It's a shortcut for figuring out what the balance is between those two charges, but sometimes it's just a lot faster. You go, take that number, put it there, take that number, put it there, done. And it makes it a little bit easier. And then there's a couple little caveats with the crossing down, like not using the 2s if they're both +2, if they're the same number, and not switching up the order of them. So there you go. I hope you have some ideas on how to write some simple ionic compounds. We'll be practicing this in class tomorrow, and have a good day.